Hello, I'm Philip Zucker. I'm excited to talk about what I've been working on today. So I've been working on binary verification for a while, and I think binary verification is useful for a number of reasons. Binary verification is applying formal methods and static analysis to binaries, things coming out ultimately out of your compilers, binary code, RISC-V, x86, that sort of thing. One reason this is interesting is because, it is easier to do verification in a higher level language, but like some low level code needs to be written in assembly for performance reasons, access to special operations, or for very tight timing or memory control. Embedded systems are sometimes kind of our most critical systems, and they have these really strict requirements, and sometimes it's unavoidable that you are writing some code in assembly. It is also a method to catch compiler bugs. If you're doing binary verification, you can confirm the compiler is producing assembly that matches your expectations from the higher level code. And also sort of interesting new one that's come up recently in the crazy age we live in. LLMs are everywhere. And the idea of directly generating assembly or binary from LLMs has been floated. And if you were to do such a thing, it's maybe not such a bad idea to have a methodology for verifying and checking that the code does what you hope it does. It's easy to make mistakes, even for humans, and you don't really know how much to trust the large language model. And it's also nice that you can give the large language model these verification tools, and it can sort of use them itself to sort of feedback, get into a good loop. It's very good to give these things like targets and feedback. They do a better job when you do that. So I've been working on binary verification for many years, and I've been on sort of this recent iteration of using my Python proof assistant Knuckledragger, which is based around the Z3 SMT solver, and also using the Ghidra pypcode semantics to get my model of what the assembly is doing. And the really nice thing about that is that it comes pre-packaged in the pypcode package, available from pip install it, and also it supports a wide number of architectures with a decent number of instructions per architecture. People use Ghidra very seriously. The NSA produced it and open sourced it, and it's a really incredible corpus of knowledge and technology that I think is highly underutilized. So I've gotten stuck in previous iterations, and there's 4 different blog posts you can read about sort of my journey of like deciding how to go about this thing. And what eventually I've sort of realized after a lot of tearing my hair out is that directly trying to interactively prove things about the symbolic executor output, even if I've cleaned it up significantly through improvements in my tooling, is still just like too burdensome. And is painful for me, and kind of it'd be extremely painful even more painful for a user of my tooling to do. So you do it that way. So the new methodology, the new way that a human interacts with the system, is instead you will write a high-level model of how you expect the assembly to work, a function that specifies how the high-level model corresponds to the level code. That connection can be automatically discharged fairly easily, and then it is the human's job to write things in terms of the high-level model of the actual unbounded properties of the code. And we've got some demos to go in today about how that all works, so here we go. So here's a simple x86 64 program, moving 1 into RDI, then adding RDI to RAX, some NOPs, whatever. Ultimately, what this program does is it adds 1. REX now has 1 more than its original value. So we can assemble this program. It's ordinary x86 assembly, using the ordinary GCC to assemble it. And then what we can do is we can symbolically execute it in order to see that what we expected is true, or to check for assertions and failures of things that we hope are true. So it's loading up. Yep. So it's loading up a little bit. And it checks. And if you like change, so here what it's checking for is that the initial value of the end value of in Rx is equal to the initial value of Rx plus 1 after you do those couple of assembly instructions. And if in fact you change it to 2, you get a counterexample found. If you change it back to 1 and like you limit the instruction limit, it doesn't find a counterexample, but it says that it didn't execute every possible pathway. So there's a incompleteness here of that. A bounded model checking will not be able to show that every possible pathway, there's no errors on every possible pathway if your program has an unbounded number of pathways through it, or extremely high number of pathways through it, and very quickly they do. But the new approach is that we specify a way of getting a high-level model of what the state is. The user specifies that. And then also the user specifies what the execution, a single execution step from label to label would be in the high level. So here we have this high-low function which says that there's a single variable of interest I, which can be found in Rex, is what it's saying. That's the state at the high level. And then the high-level summary of what this function does is it takes in a state I and returns the state where I is one more. And then we can automatically discharge that this high-level model is saying the same thing as the low-level code. And what that is kind of doing, I kind of like this diagram, so I want to show it, is we specified just now this high step function. Lifting the assembly specifies this, oh, you can't see it in the, oh, there it is, okay. We just specified the high step function. The low step function is a thing that is changing all of the registers and all of memory and all of that, and that is lifted directly from the assembly and is accurate to the assembly. What the property that was just proved says is that if you take an initial state of low state of all registers and all memory and stuff, you can step it using the symbolic executor from one label to another, and then you can lift using our specification of the correspondence of the low state to high state into a high state. If differently you chose to lift the initial state and then step using our specification of the step function, doing those two things should be the same thing. That's how you state that that the high-level spec is actually in lockstep, is doing the same thing as the low-level execution. Okay, and in order to do that, you only really need to consider finite trace fragments. So there's no inductive argument really needed exactly to discharge this sort of idea. Well, the inductive argument is sort of implicit. It is not exposed to the solver. The solver just is given, 20 pairs of high step, low steps, and discharges all of them. And then we can also do interactive proofs over this thing. This is an extremely simple example, so actually you don't need to be doing interactive theorem proving on it, but here's kind of what it looks like. I want to say that the step function does return I plus 1. Well, I can, these are tactics for doing interactive theorem proving. You can fix the variable here. Then you can unfold, by default step is an opaque function. You can unfold that function, and then you can call the SMT solver through auto. And here you get back an actual proof object that, step equals I plus 1. Step for all I, step of I equals I plus 1. Now that was very toy, so let's get a little less toy with memcopy. And this is the one that's sort of, I could scale to a couple things that are a little more complicated than what we talked about before, but once I got to this, things were getting just hairy enough that I needed to switch gears into this new approach. So a slightly more involved program is memcopy, where you are given a length, a source pointer, and a destination pointer, and you want to copy length bytes from the source pointer to the destination pointer. An array of size length that starts at source. And memcopies are very often written in assembly because they need access to special opcodes, or you want to do loop unrolling. You want to be very careful about how these things work. Sometimes there's complicated dispatching of, do you need to copy a single byte, or do you want to, if one's length gets large enough, you can copy entire words at a time, or maybe you can start using vectorized instructions, or all sorts of things. So, and memcopy is used a lot, so it makes sense to like really optimize it. So here we have this thing. It's a loop. You load from the source, you store into the destination, you increment those pointers, you decrement length, and then you possibly are done, or you branch back. Okay, so that's how that works. Okay, and then we can assemble it with this slightly goofy looking command, because this is now RISC-V assembly instruction. I guess I didn't mention that. Because I'm working on the Ghidra pypcode semantics, I get a lot of ISAs for free. There's like 20 or so supported ISAs. Then we can symbolically execute this thing to see that, here's the property that A2, that the length, which is held in A2, is always less than or equal to the original value of A2, the argument given. And oh, it went red. Red? What does red mean? Counterexample? What? I actually played a little trick on you. If you're paying attention, you may have noticed this was called my copy bad. Maybe that's, leading a little bit. But actually, the thing is, in that version of my copy, we left out this initial check. If the length is 0, and you don't do this initial check, you'll actually wrap length back around to, the maximum integer, 2 to the 32 minus 1, and the property no longer holds. So it needed this initial test. And actually, this bug is very much related to one that I've seen in a real code base, and is sort of the impetus for some of this project. These things do happen. It's hard to write perfect assembly, and it's hard to think about all the cases. And this is like, not a complicated bug, but when it's buried in 100 or 200 lines of assembly that someone else wrote, it can be kind of hard to recognize. Okay, so here's a version that has this branch in it. We can assemble this version, and then we can model check it. Okay, and we run, and it gets down here, and node counterexample found in 25 instructions. Awesome. Does that mean there's no count? There's actually no bug? Like, what about 26? What about 27? What about 1,000? What about 10 billion iterations? This says something about the first 25, but it doesn't say anything about after that. It doesn't imply anything about after that. And if you want to go to that next level of assurance, unbounded verification, you need to sort of switch gears a little bit, and bounded model checking and symbolic execution kind of just mostly aren't going to cut it. You need to sort of be able to get a little more hands-on. So we're going to do what we were talking about before. We're going to write a high-level version of the state, specify how the low state connects to the high state, and write a step function over the high state. So the high state here is this tuple, this struct, of a PC, a program counter corresponding to which label you're at, all of RAM, and then a length, a source, and a destination value of what you're currently working at. And the way that this is connected to the low state is that the source pointer is held in A0, the destination pointer is held in A1, and the length pointer is held in A2. And the entirety of RAM is copied into the high-level RAM, which is kind of what is needed in order to specify properties about where things are written to. And then we will write a high-level step function, and it's written in Python syntax, and it's using the Knuckledragger reflection facilities to actually convert this into a logical formula. I think it's really important that specifications are readable, and Python syntax is readable, or people are familiar with it, and it's nicely syntax highlighted and all that. And so I think there's a good reason to actually be doing it this way. And it's once these things start getting big, they kind of need to be readable. And the raw syntax for doing this, using Knuckledragger as a library, constructing SMT formulas by hand, or constructing these expressions by hand, I can kind of read it. I'm good at it, but it's not as readable as this. Anyway, so here's the execution of a single step of the high model. If the program counter is at my copy, the start of the program, we check if the loop is 0. If it is, we go directly to done. Otherwise, we go to the start of the loop. If the program counter is in the loop, first we actually do the copy. Then we decrement the length counter. We increment the length value. We increment the source pointer. We increment the destination pointer. If length is 0, we go to done. Otherwise, we go to the start of the loop again. If the PC is done, then we just stutter, which is a way of sort of saying the thing is finished effectively. Okay, so we have this model. Did I already execute it? I think not. Okay. And now we can discharge the bisimulation between the low and the high code. And it automatically does it very quickly. Z3 is a really impressive piece of work. There are these different pathways through the program, and each of them had a query that was discharged saying this high step is the same thing as the symbolic executor's step. And finally, we can define the transitive closure of this step relation using kd.trans, the transitive closure of this relation. And we can then specify properties about all time. And we can prove them using an inductive argument, a manual inductive argument. So here is an inductive argument that the end of the array at source is always the same. The end of the array at dest always stays the same. When you increment the source pointer, you're also decrementing the length pointer at the same time. So actually this value of the source plus the length stays the same the whole time. And the proof is very mechanical. There's nothing interesting going on here once you know about these sorts of things. You fix t, you say I'm going to induct over all time, and then there's 3 cases here of the different cases of time being less than 0, which is not interesting, time equals 0, which is at the initial time step, and time greater than 0. And they basically work by unfolding the definition of the step function and then calling auto is calling Z3. And at the end, you do get this proof statement that this proof object that the property holds. And then here is the analog of the length property before, but you may notice it looks a little more complicated. Actually, it turns out that this property on its own is not strong enough to be an inductive invariant. So I'm going to discover that actually you need to strengthen the property that it's well, I've written a slightly more complicated property here. How about that? And you can manually do the thing in a similar way. It's actually quite mechanical, and nothing too interesting is happening in this proof. And actually, this is astonishing that nothing's interesting is happening in this proof, and it's because Z3 is so powerful. Once you've given it the induction step, it's incredibly good at discharging these individual things. If you had to do a similar proof in ROC or other systems that don't, well, I'm not going to pick anybody, but in a system that has less automation, it'd be a lot of work to like actually manually do all the bits and pieces that go into this. So that's kind of it. And admittedly, doing these manual proofs is more work and more conceptually complicated. And a lot of value can be done by using boundary model checking, test cases, unit tests, etc. first. And these should be done first. But if you really care about that extra, extra level of assurance, you do kind of need to go into these unbounded things because basically no non-astronomical number of tests or bounded model checking or fuzzing is going to be able to prove that things can't be found, that things can't go wrong. Thank you. That's it for today.